So we'll pick up where we left off. What makes the Earth warm? We learned there are only 3 ways the Earth can warm. From the outside, from the inside, or in the middle. And then we're left within the middle because there's scientific evidence that's showing the other 2 aren't going to be significant. So we talked a little bit about the percentages. I think it's just important that you know that the energy that we're really worried about is this reflected energy. Remember that not all of this 45% is going to go into our atmosphere. Some will go out. The heat will go out into outer space, but a lot of it will be kept here. And the Earth has been fairly stable since man has been here, right? The temperature has been pretty stable. We've been in a very stable climate period. A lot of people think, oh, this is just something new that people have thought about. But actually, in 1896, savant Arrhenius, who was a thermochemist, he invented what's called the Arrhenius equation. So he was very interested in heat energy, thermal energy, and chemical processes. And he was talking about the ice ages. And he was the first scientist to attempt to calculate how changes in the level of carbon dioxide in the atmosphere could alter the surface temperature through what's called the greenhouse effect. Now, the greenhouse effect basically is that as the solar radiation comes in through the atmosphere, it bounces reflected off the Earth's surface, and those what are called greenhouse gases, or those molecules, make the atmosphere like a greenhouse and will insulate the Earth. And he knew that if the quantity of carbon dioxide would increase, the temperature would increase nearly in arithmetic progression. And so he knew this. Remember, this was at the beginning of the Industrial Revolution, and his work is currently seen as the first demonstration that global warming should be taken as a serious possibility. The next person that talked about this was James Hansen. And I want you to listen to this short video. I think it's absolutely fantastic. He's actually from Houston. He's a NASA guy. And he was one of the first scientists to say, you know what, I really think we have something we need to worry about here, and let's listen to this.
In 1988, James Hansen gave some groundbreaking testimony in front of Congress, where he said for the first time that the signal of human-caused global warming is discernible outside of the variability of climate.
Based on what we knew in 1988, Jim Hansen was out on a limb. You could have reached an alternative conclusion fairly. And in fact, if you look at the 1990 IPCC report, their attribution statement was that the system was warming. It was consistent with global warming, but it was also consistent with natural variability. He was kind of out on one end of how you could read the data. But it turned out he was right.
Our best estimates of natural climate variability can't come anywhere close to matching the size of the warming signal that we see, that we measure, that we monitor. That seems like an important thing to state very clearly.
Amazing. I mean, Hansen has been remarkably prescient when it comes to the predictions he made decades ago and what's actually played out. He predicted essentially the warming that we've seen 3 decades ahead of schedule.
Well, Hansen got it right, basically, because by now there is no more doubt that we are observing the signal of global warming. It has really very clearly emerged from the natural variability in the climate system, and also the projections for the future that Hansen published at that time, they have turned out to be correct.
And so Hansen looked at 3 different scenarios. Scenario A that had very rapid increases in greenhouse gases and very rapid warming, a scenario B, which had much more modest increases, and a scenario C, which had essentially no increases in the future. And so now we can actually compare what's happened to what Jim Hansen projected. And so of all the scenarios that Jim Hansen produced, the scenario B is closest to what's actually happened.
And the warming that he predicted, that scenario, is an eerie match to the warming that we've actually seen.
Back in 1981, Hansen had produced another paper where he had projected future temperatures. And those were quite close to what we've observed today. In fact, slightly too low.
Well, the actual temperature rise
since my first major paper in 1981 has actually been faster.
We did an exercise recently where we looked at all the climate model projections that have been published since 1975. So there's a paper in 1975, in 1981, in 1988, in 1990, 1995, et cetera, that all had climate model projections for the next few decades. And we compared them to observations, both before they were created and after they were created. And it turns out they all match up remarkably well with what's actually happened.
Globally, we've seen warming of roughly 0.18 to 0.2 degrees Celsius per decade. So that's nearly 3/4 of a degree Celsius over the satellite era, global scale warming. And that our best estimates of natural climate variability on that multi-decadal timescale.
He also successfully predicted the cooling that we would see. The Pinatubo erupted back in 1991.
He recognized, well, I can look at that. It's a test that their model did pretty well. So when given the actual aerosol from Pinatubo, as observed from space, when you put that into the Goddard climate model, the model produced this rapid cooling. It pretty much got the maximum surface cooling that we had actually observed in the real world. And importantly, it got this long goodbye. It got the recovery of temperature to pre-eruption levels pretty well. And you got to get a lot of physics right in order to get that recovery timescale right.
And yet, Hansen, using this fairly crude, decades-old model, made predictions that have borne out, that have stood the test of time. And it's reason to take very seriously the predictions now that are being made with climate models that are actually far more sophisticated and detailed than the ones that Hansen used decades ago.
We are now in a climate system where the impact of his emissions is so strong, so clear, that nobody in the scientific community denies it. And when you get to that point in science, that's pretty strong. But the real debate should really be about what are we going to do about this, rather than talking about whether it's climate change or not.
It's interesting to note that James Hansen had death threats in 1988. And when he talked about this, people were so upset about it that they threatened his life. And he was down at NASA here in Houston. And interesting, the response that people had a real visceral response to this data, even then. All right, but let's talk a little bit. So what I want to dedicate this day to is, how do they know? When I remember when I first started teaching this class, I was like, how in the world do you know what the temperature was, 800,000 years ago? That was my big question right off the bat. That was what I didn't understand. So I want to talk about that. I'm going to start off with current technology. Very interesting. I could get lost in all this stuff. But currently the Earth is monitored, its temperature. Well, first let's look at carbon dioxide concentration. So scientists are measuring the carbon dioxide concentration. You can see here that as we go up, here's 2088. You can go all the way up. I think this map only shows us to about, actually this is February 2021. We're at 415 ppm. I remember back when we were worried about getting to 400. That was kind of a dangerous number. Think about how we have increased the amount of carbon dioxide. And remember that correlation, right? Remember that correlation between temperature and CO2 concentration. If we look at this, I thought I could pull this up, but I guess not. So we're going to start at 2002. So these grays and these colors are, in the 300s. Remember I said it started around 350. And then as we go in time towards 2016, this data shows you can see it warming. Now I want you to note that it's not warming. The CO2 concentration is not evenly distributed around the Earth. It's being distributed, but there are places where it has higher concentrations than others. One of the things you might want to note is that the concentration of carbon dioxide in the poles is very high, especially in the North Pole. And we'll talk later again about why in the world that is and why we keep hearing stories in the news about, ice glaciers snapping off and melting and icebergs and all that kind of stuff. You can see that we're getting higher and higher concentrations. We're up into the 400s when we get red. We're almost to 400 when we get to that. And if you look back 800,000 years, we've not been here before. Not really. And so that's an issue. As we increase this carbon dioxide concentration on our planet through the burning of fossil fuels, what does this mean for temperature? And of course, the average temperature of the Earth is going to lag behind this somewhat, right? As it shoots up, it's going to take the Earth some time to catch up. Now, how do we measure these things? So there, I just thought I'd show you this. I thought this was so interesting. There's a satellite that is up in the atmosphere, and it will measure the concentration of carbon dioxide. Here you go, 2020, tied for the hottest year on record, matching 2016 NASA found. And so I thought that was interesting. Let me pull this down here. I'm going to go back. Sorry about that. Let me get my websites all straightened out here. We're going to pull this back up again. Okay. All right, here's some more pictures. This is Orbiting Carbon Observatory number 2. I wanted to show you the instrument that's being used because I thought this was really interesting considering what you learned yesterday. So basically what they're doing is this satellite is able to measure how much radiation is going in and how much is leaving and determine whether or not that is changing. And there is carbon dioxide absorbing, right? So it's coming in, bouncing off, and then this is measuring. Is the difference between the amount of infrared radiation going in and reflecting out changing? Because if that's going down, then we know that more heat energy is being trapped in our atmosphere. And the only way that can be trapped in our atmosphere is through carbon dioxide. Very interesting. That's something I didn't know much about. And then we can look at temperature. Also, there are ways that we are monitoring temperature, so I wanted to show you that as well. We used to, back when I first started teaching apes, we would look at the National Buoy Center. There are buoys all over the planet. There are thermometers all over the planet. And these are Earth temperatures, so all these are places where you can click on them. They're kind of cool. I don't know if I can do one now on this, but you can click on them and you can go to any of these buoys and find out exactly what the conditions are at that point. We are also measuring the temperature of the planet with satellites. So there's a lot of technology that has been in the picture with this, and so I think that is interesting to look at. What I was interested in, however, was how in the world were we measuring CO2 concentrations back in the past. So what we're going to do is we're going to look at historical records. That's one way. But remember, this is not going to go back real far. But people took very, very data-driven notes about their climate because it had everything to do with agriculture, food production, ship travel, all of that. So a lot of these records go back far and are very detailed. What we're really interested in, though, is when we go back really far, we can even go back millions of years, is what's called proxy data. It's not strictly climatic, but provides insight through indirect evidence as to what climate is. Tree rings, sediments, ice cores, fossils, pollen, corals, and carbon-14. So when we come back with our video, we'll talk about those.